Hi everyone, welcome to our second video on sample size planning concepts. This is part of a sample size planning workshop hosted by the North American Society for the Psychology of Sport and Physical Activity. And again, these videos are meant to be kind of asynchronous complements to the things that are done live in the workshop, so you can always come back and refer to these things later. Or if you're not attending the workshop and just viewing this video for the first time, hopefully there's some useful stuff in here for you as well. In our first video, we kind of defined statistical power and talked about its relationship to null hypothesis significance tests. In this video, we're going to talk about kind of building up some statistical intuitions about power analysis while glossing over the details of a lot of calculations. And in the subsequent videos, we're going to be writing some R code to show how you can simulate a power analysis for a number of common different designs and statistical tests that you might be interested in. So in this video, I really want to talk to you about like intuitions versus precise answers, because statistical power and sample size calculations can get very complicated very quickly. A lot of times people come to me as a kind of consulting statistician in the design phase of their study, and they have, all kinds of covariates, or they want to have this extra factor, and they're looking at this, 2 or 3-way interaction, and all of that stuff gets really complicated. Power analysis is not quick and easy. It is not something you do in a couple hours on a rainy afternoon. There's a lot of things that go into it. You have to evaluate all of your assumptions, and you have to have a good understanding of how to get the answer that you want. And even if you have a closed form solution and can use a power calculator, right, usually your answer is going to be imprecise because you're basing it on some assumptions. And a lot of the time, there might be some very novel aspects of your design or some missing information that you can't actually do it in a closed form way with a power calculator. And then you need to write simulation code in order to simulate the design a bunch of times, run a bunch of different statistical tests under different sets of parameters, and see what your best guess for your statistical power actually is. So again, not a simple process, and I would highly recommend you work with a statistician when you're designing your study in order to do your power analysis and make sure you can design your study in the best way. But that said, right, we don't often get perfect answers for our sample size calculations anyway, so I think it's really important to build up some statistical intuitions. You can then consider kind of a range of assumptions when estimating the sample size, right? And then your power analysis, remember, is only going to be as good as those assumptions. So the key thing is not to find a set of parameters that give you the answer you want. The key thing is to test reasonable parameters that you think reflect reality, right? The reality that you want to go out there and test. And then you have to think about how you're going to deal with those consequences. So in this video, I want to build up two intuitions in particular. One is about what kind of effect are you trying to study? And the other is how many observations do you think you will need? Because these are two things in my personal experience that people underestimate a lot. And certainly I know in my growth as a researcher, I got very wrong early on in my career. So intuition number one, what kind of effect am I trying to study? Often, researchers will tell me something like, we don't know how big an effect is because we haven't done the study yet. And therefore, they can't do the power analysis. Or the data just don't exist for us to decide, what to put into the power analysis. I'll ask them, well, what would be the mean difference between these two groups? Or what would the standard deviation be for this variable in this population? And the argument is basically, we don't know because we haven't done the study yet. But I'm going to show you that I don't think this is a really good line of argumentation. And to do that, I'm going to use a totally different example where I want you to help me find a dragon. Let's say, I want you to help me find this dragon. I'm putting an expedition together. I'm showing you on a map where I think the dragons live, and I want you to come help me find them. And I use this example because the phrase, here be dragons, or in Latin, hic sunt dracones, was a phrase used to indicate like dangerous or unexplored territories in medieval maps. Plus dragons are just, really fun and cool. So, okay, now imagine I'm trying to sell you on my expedition to find a dragon. We were meeting in some wonderful fantasy style tavern, right? I have a beautiful parchment map that I unrolled on the table. It's got jagged edges. I'm trying to, convince you to join this quest to help me find the dragon. You might reasonably have some questions, such as, where does this dragon live? Does it live in the desert? Does it live in the frozen tundras of the north? How big is it? Is it tiny and cute, or is it massive and fearsome? What are the risks? What kind of tools will we need if we're going to try to apprehend this dragon, or even just keep ourselves safe while studying the dragon, right? And if, as you're asking these questions, I just keep saying, well, we don't know because no one has ever seen one. We don't know because no one has ever seen one. We're just going to go kind of walk around for a while and hopefully we'll find a dragon. But when we see a dragon, we'll know. That probably wouldn't be very satisfying for you. And you would think that my quest is kind of a waste of time. So when researchers say something like, we don't know how big an effect is because we haven't done the study yet, I think they're kind of asking the wrong question. It's not really helpful to say, well, what is the precise effect, or what are the exact values that we need to plug in here? Because you probably wouldn't know that even after you ran the study. You're sampling from a population. So any estimates of the effect size that you get are going to be estimates. Any estimates of the variances that you get are going to be estimates. We can't be precise, and it's not really a great expectation to have from the get-go. So instead, we should maybe ask questions like, what is the smallest effect that would be reasonably important? Or, given the budget and that I can only get 100 people, what is the smallest effect that we can reasonably study? So these are going to be more helpful questions for you as you are thinking about the kind of effect you're trying to study. And now, again, in case it wasn't clear, the dragon in my metaphor is the hypothetical true effect out there somewhere in the world, right, that exists that we're trying to study. So when we think about, approximately where does the dragon live? In more realistic terms, that could be mapped onto questions like, are there certain individuals or conditions in which we expect the effect to be strongest? Could we then use tighter inclusion or exclusion criteria to reduce background variance and strengthen the effect? So essentially, we're getting the best ratio of the effect size to the variance. Again, how big is that dragon? Well, is there a minimum clinically important value for what we're trying to study? If I'm trying to study, whether something is going to have a meaningful change for a person's readmission to hospital, right? Maybe any amount of readmission is worth knowing about. Alternatively, if I'm doing some kind of sports supplementation study and I want to see if something makes a person's VO2 max, go up, if it only increases by 0.5 points, even if it does that very reliably, that's not a really meaningful change in VO2 max. So maybe I want to make sure that it's going to change by at least, 2 points. And if it changes by 2 points, then I think that that's worthwhile. We can similarly ask, how much background noise would we expect? Because again, we're going to have that kind of yardstick of a minimum effect that we're interested in, but that effect size is always relative to the variability. So how much variability would we expect on our primary outcome in the population that we're trying to measure? And if we don't know that, it's going to be really hard to design a study, right? But I bet that information is out there. Usually people aren't inventing outcome measures for the very first time while they're also doing a trial. That outcome measure has probably been studied in some other context, and there's some meaningful information that we could use to think about how we're going to apply it in our own study. And when we're balancing these things, it's important to be conservative and take the low-end estimate, right? Because if we think an effect is much bigger than it is, there's a chance we'll miss it. But if we're conservative and we go with the low end, not only does literature show that there's a biased distribution of effect sizes out there, and published effects are usually massive overestimates of what the real effects actually are. But even that publication bias aside, if we're conservative and we kind of lowball our estimate, then we can be sure that we'll detect the effect if it exists. Whereas if we're too optimistic, there's a good chance we'll miss our effect because we're going to end up designing an underpowered study. Then, okay, what are some potential risks? In a real experimental context, this might be, well, what happens if we have a false negative and we miss an effect that exists? What happens if we declare an effect and we're wrong and instead we make a false positive, right? And depending on the phase of the research, the relative costs of these two things could be very different. And we have to also balance that with the costs associated with the study. So for instance, if I'm doing some very early phase investigation into a sample of healthy young undergraduates, I might not be that worried about a false positive as compared to a false negative. Because, if I have a false positive, the next step would have been another study anyway, right? Where we're probably trying to now better understand this effect or test some moderator of this effect. And if it's going to be another sample of 100, healthy young undergraduate students, that's a bummer. No one wants to waste their time, but there's not a lot of money or resources wasted on a false positive at that stage. So early stage investigation, you might tip the scales a little bit more toward, worrying about missing an effect that exists than you are worried about the cost of a false positive. The reverse might be true, though, at a later stage investigation, right? Where if we're doing a really large, phase 3 clinical trial, we want to be very sure that we don't have a false positive, because our result is probably going to go on to influence policy and potentially change clinical practice. So the farther we get toward that confirmatory end of the translational research pipeline, now the costs of a false positive are going to greatly outweigh the costs of a false negative, because the next step isn't just, another study to advance our understanding. The next step might actually be interventions, right? And really changing policy and practice. So we have to balance the costs of those two particular errors, but we also have to think about the costs, again, of the particular study, just literally how much is going to cost to buy the equipment, to pay for your participants to come in, to pay for the assays that you have to take if you do, biological samples, right? The higher those costs are, the more careful we have to be with some of the concerns up here. If these costs are relatively low, maybe you can be a little more cavalier with some of these things here, right? Because again, if I'm doing a online survey-based study and it's relatively easy to get more people, I might be able to really iterate from one experiment to the next. And if I don't see a result, maybe I can design my study in a slightly different way, go in with a revised version and then say, yes, okay, we learned from that previous mistake. Now here's how we're going to operationalize this. We're going to take a new sample and we're going to study it again. In contrast, if it's costing me hundreds of thousands or millions of dollars to do this study, my funder is not going to have the patience for me to be like, hey, we learned a lot from this negative result, and I think now in round 2 with these revisions, it's going to be much better, and you should give me another $1 million for me to figure out if that's correct, right? So we have to balance those costs as well when we're considering the study that we're about to embark on. Again, what kind of tools do we need for studying dragons? Well, in real science, that probably maps on to do we have reliable and valid outcome measures? If we don't, no sample size calculation is going to be really helpful because if you have an unreliable measure, it's a non-starter to begin with. There's no point in really doing much of anything with a non-reliable measure, right? So hopefully all of your measures are going to be reliable, but it's really going to be critical that they are valid, because if we are measuring the wrong thing and we're measuring the wrong construct, it's possible that our intervention has an effect, right? But it has an effect on something that we did not measure or that we measured poorly. And that's going to be a real problem and potentially lead to a waste of money and resources. Similarly, then we have to consider the most cost-effective way of collecting the data. If I want to study people's walking, can I do that with a Fitbit sensor? Or do I need to bring them into the lab and do 3D motion capture, right? What is the thing that I'm trying to measure? And what is the most cost-effective way to do that? Similarly, what is the most cost-effective way to do an intervention? If it is something that can be meaningfully studied online remotely over the internet, do I need to bring people in? Right? These are all questions that we have to answer, because if I'm going to be spending more money to bring people in and I have to bring a lot of people in, there's going to be some trade-off now between, all right, well, I can't get 400 people in the lab, but maybe I can get 400 people online. So is there a meaningful way to do this online where I can actually increase my sample size and have the power that I need? So these are all questions, right, that you should be thinking about when you're designing your study. And these are all things that, you need to be balancing against each other when you do your power analysis, or talking through with your statistician when, for more advanced designs, you're probably going to be working collaboratively with a professional statistician to do a power analysis. So if you can answer these questions, I assure you, you have more information than you think. And that means you can probably design a better study. So don't fall back on that, safeguard of if we wouldn't have to do the study, if we already knew the answer to these questions, because you're going to have lots of useful information that can go into a power analysis, and it's going to help you walk through a bunch of different scenarios about what reality might look like, and then think about the exact sample size you need. And again, to extend my metaphor, if you'll indulge me for a minute, the surest way to miss a dragon, right, is to look in the wrong place, not look for long enough, and just not know what a dragon looks like. Right? So you need to make sure that you have some information about dragons if you want to go out and study dragons. And if you truly don't know anything about dragons, you probably shouldn't be studying one yet. Okay, intuition number 2. How many observations do I need? So now that you've grappled a bit with like, what kind of effect am I trying to study and how can I study it? How many observations do I actually need? And I think people are always surprised by the number of observations that they actually need in order to reliably see statistically significant results. So, as one analogy for thinking about this is in measurement theory and reliability. So if you think about like signal to noise in some biophysical signal, right? It could be an EMG signal, it could be a motion sensor, whatever it is. The noisier that signal is, you're going to need to take a larger number of measurements in order to get a reliable result in the end. So the number of measurements is proportional to the noise to signal ratio, right? Or the inverse of the signal to noise ratio. And to give you an example of that, let's say here's y as a function of x, and I've taken 5 observations. It looks like there might be some negative, linear relationship between x and y. If I take a few more observations, right, okay, it still looks like there's some kind of negative, maybe nonlinear relationship here. If I take more observations, it's definitely there's some non-linearity below about an x value of 2. It's almost like it's increasing. After 2, it's like it's decreasing, right? And eventually, if I take enough observations, even in this very noisy signal, I can actually see what the true underlying signal is, right? So if I add observations, random noise cancels out, and the true signal becomes clearer. And in this case, there's a sinusoidal relationship between x and y. And once I take about 60 observations, that's super obvious. Whereas when I had 10 observations, that's not obvious, and I couldn't tell the difference between a sinusoidal waveform and just a linear trend. The same principle is going to apply when drawing random samples from a population. And like we talked about in the last video, there are a few different factors that are going to affect statistical power. The effect size and the sample size are going to affect power positively, whereas the variance is going to affect power negatively, because it's going to be easier to detect large effects. It's going to be easier to detect effects with large samples, right? But if you have highly variable data, it's going to be much harder to detect those effects holding other things constant. So one way we can rewrite, our sort of signal processing proportion is to now say it's not just the number of observations, but the sample size, which is, again, really the same thing if a person is the observation. But where the sample size is going to be proportional to the noise, right, which we might think of as like the standard deviation or the residuals over the size of the effect. This could be a mean difference or it could be a slope. And then we are going to square these things to keep this proportion correct. But this is the proportionality that we're interested in now. Alternatively, you could write this as the sample size is inversely proportional to the effect over the standard deviation. And you might be a little more familiar with looking at it this way if you've calculated something like a Cohen's d, because there you're taking the mean difference and dividing it by the pooled standard deviation. Either way, it's mathematically identical, right? But I like writing it this way because I think it makes it clear that if your variance gets larger, you're going to need bigger samples. And if your effect gets smaller, right, you're going to need bigger samples. So writing the proportionality this way, I think, makes a lot of sense. We can then try to really determine how many observations that you need. So for instance, this is an output from G power, where we're looking at independent samples t-tests, right, for the difference between two groups. We can get the total sample size here on the y-axis as a function of the effect size as a Cohen's d. So again, Cohen's d is the difference between the two groups, right? That mean difference divided by the pooled standard deviation. So 0.1 would be a tenth of a standard deviation difference. 0.5 is half of a standard deviation difference, and a 1 is a huge effect where you have a difference that's equal to 1 full standard deviation. The two different lines that I'm drawing then are for 90% statistical power in blue and 80% statistical power in red. And you can see that when effects are quite small, we need thousands of individuals, whereas when effects are quite large, we might only need tens of individuals. So it's kind of hard to see this all on the same scale because just the orders of magnitude are so different. If we zoom in a little bit and just look at the effects of size 0.5 to 1, you can see that there is some differentiation here, especially between the 80 and the 90% power. So if we have a really large effect, right, if it's the mean difference is 1 standard deviation different, for 80% statistical power, we're only going to need 34 people. In contrast, if it's half a standard deviation different, right, for 80% statistical power, we need 128 people. So that's a pretty big swing, right? Do I need 34 or do I need 128? And we need to be able to estimate that Cohen's d and have some idea, how big our effect is. And if you have data from previous studies, obviously that's a great place to start, and we'll be looking at that in some of our previous videos. But right now, I just want you to be able to visualize a little bit more. Well, what does it really mean if the effect size is 0.5 or 1.0 or 0.8? How big are those effects? What would those data look like if we graphed them? So here's an example where let's consider a huge Cohen's d of 1. The n required for 80% power is 34. If we had a population with a Cohen's d of 1, so these are hypothetical populations of individuals in a control group in blue and a treatment group shown in brown, that are separated by 1 standard deviation. So in this case, I think they both have a standard deviation of about 10, and their means are 10 points apart. So the Cohen's d is 1. What this means is, if I now draw a random sample of 34 people, I'll pretty reliably get separation between those two groups, right? If I take another sample, I'll get that separation. And if I kept taking samples, right, basically across samples, I'm going to pretty reliably see this difference if I take samples of at least 34 people per group. If this effect gets smaller, right, and now we're taking a Cohen's d of about 0.5, the n required to have 80% statistical power is 128. Right? At the population level, you can see how much closer these distributions are and how much they actually overlap, even though they're half a standard deviation different. And when Cohen put forward his sort of rules of thumb, which he never really intended people to use as widely as they do, he talked about descriptively that 0.5 was maybe a moderate or very common effect in psychology, which was the literature he was working in. So 0.5, might look like there's a lot of overlap here, but this is actually probably even maybe optimistic of a lot of effect sizes we might be trying to study in the scientific literature a lot of the time. So this is a huge amount of overlap, but this is probably the reality of our situation a lot of the time, and that means we're going to need quite big sample sizes in order to see that difference reliably across studies. So for instance, if we underpower and we now only take 34, which was appropriate for studying a really big effect, we're not reliably going to get mean differences or statistically significant mean differences in one sample. In this sample, looks like maybe we did, right? But if we kept sampling, we're going to get a lot of samples where we don't get a statistically significant difference. We might not see any mean difference at all because we are tremendously underpowered for the effect that we are trying to study. Instead, if I take this sample size way up, and now I'm powered for a Cohen's d of 0.5, I can take 128 people in one sample, 128 people in the next sample, right? And if I keep taking samples with 128 people, I'm reliably going to see a statistically significant difference between those means. And specifically, right, with 128, and assuming that the real effect is a Cohen's d of 0.5, I will see statistically significant mean differences 80% of the time, because that's what it means to have 80% statistical power. Finally, what if we wanted to study something quite small, like a Cohen's d of 0.2? Well, it says we need 788 people in order to do that, right? And this is what it would look like at a population level if we thought our groups were 0.2 standard deviations apart. There's a tremendous amount of overlap in those two distributions. There's not very much of an effect, right, in a practical sense, if we think about the difference between these two distributions. Rather than recruit 800 people, right, can you do something to make the effect bigger or the variance smaller? Sometimes the effect might be out of our hands. So, well, there's nothing really that we can do to change the mean difference. Maybe that's a fixed thing. But maybe we can reduce the variance to make the Cohen's d and the standardized effect size bigger. Right? So if there are things that we can do in terms of our inclusion-exclusion criteria to shrink the variability of those distributions, or maybe some things that we can do through the use of covariates to control for some of this residual variation and make the difference look bigger proportionally, right? Maybe we can actually get that Cohen's d to be bigger and we don't need to recruit 800 people. Certainly it's going to be more cost-effective to increase that effect size or reduce the variance if we can through our experimental design. However, we also have to be realistic, and those things aren't always under our control. So if the best of our evidence and reason tells us we are trying to study something that is quite small, we might just have to bite the bullet and figure out how we can get a big enough sample, or we have to move on and decide we want to study a different question. Okay, so to recap, we've talked about the complexities of power analysis and different designs and why it's important to build up our statistical intuitions. We also discussed important questions to ask yourself when deciding what kind of effect you're trying to study, reasoning through those things for yourself, but also working through those questions with a biostatistician if you're able to consult with a statistician while you're designing the study. We also introduced some rough ideas about how many observations you might need when trying to study effects of different sizes. In subsequent videos, we're going to introduce simulations for more complex designs, which actually allow us to avoid some of these standardized effect sizes like Cohen's d, partial eta squared, Cohen's f squared, right? If we can actually just enter in means, standard deviations, correlation coefficients, I feel like those things are a lot easier to understand. And in subsequent videos, when we're running those simulations, we're really going to try to help you put in the values that you think, and then maybe change those values to run a more optimistic simulation or to run a more conservative simulation.